Alrighty, welcome to section R.2. So we're only covering objectives 1 and 5 in section R.2, and one of the first things we're going to look at is something called the number tree. That's not the main name for it, but that's what I like to call it. We're going to look at the different types of numbers there are in math and what they're called. So let's go ahead and start with this, what we consider the smallest group of numbers, which would be called the natural numbers. Now, natural numbers, if you think about when a kid starts counting, how do they start counting? Right? They start counting from 1, 2, 3, 4, and 5, right? They don't consider 0, they don't consider negative numbers, and we don't think of fractions as a kid, right? The natural numbers you start counting with. So that's the set of the numbers of 1, 2, 3, and so on. Now, natural numbers falls underneath something that we call whole numbers. And the only thing that whole numbers really contains that's different than natural numbers is it also uses or also contains 0, which is how I remember whole numbers, because whole looks like a 0, wholes are zeros, right? Okay, so whole numbers, all you do is you add in that 0, and there you go. Now, the next group of numbers that contain whole numbers and natural numbers are called the integers. The only difference with integers is it also contains the negative numbers. So we can go -2, -1, 0, 1, 2, and so on. Okay, so inside of integers we have natural whole numbers, and so on. And then, let's see, after integers, what do we have? We have things called rational numbers. Okay, and what are rational numbers? Well, in the word rational, we have that term ratio. And ratio, if you recall, is a fraction or a ratio between two numbers. So we have fractions. So in rational, we also get to plop in the fractions. So any kind of fractions you can think of. If you can write, fraction with it, or maybe a decimal that stops, and so on, those are rational. All right, so those all fall under something we call the real numbers. And there's one other group that falls under the real numbers, and he's over here on the side, kind of the oddball. This one are called irrational numbers. And those guys are the numbers that cannot be written as a ratio. For example, one of the most popular ones everybody knows of is pi, right? We know of it as 3.14, but that's just an approximation. It is a never-ending, non-repeating decimal that goes on and on and on. That would be an irrational number. Another one would be maybe the square root of 2, and so on. So all the numbers that cannot be written as a fraction or a ratio of two numbers falls into the irrational category. And there we have the family of real numbers that we use for math. All right. So something that we're going to look at is something called set notation. I was already using it up above here, these little sort of braces going on the sides. Basically, what this tells us is a group of numbers that we are looking at. So for example, most of the time, set notation uses the little braces and then some numbers inside. If I wanted to state that there was a number inside the element, I could say maybe that 2, and I'll use this symbol here, looks like an odd E, is an element of what? Well, maybe 1, 2, 3. That is stating that 2 is inside of this little set. Okay, another thing that we would have for set notation is we have the symbol here, the 0 with a slash through it. Please note, that is not 0 in math, so if you use that, I will assume you are saying the empty set. Okay, so be careful not to use that in place of 0. That is a symbol for the empty set. We also might use this symbol here to indicate an empty set. We have the braces and nothing inside of it. That is also the empty set. One other thing we can do for set notation is we can say we have a bracket, we have some variable x, and we use this symbol here for such that x is, and then we state some property. So maybe if we said x is even, then we know this is a set of all the numbers that are even. Now, why wouldn't we just write out all the numbers instead of using this weird notation here? Well, the thing is, could you plausibly write out all of the even numbers in the world? No, there are infinitely many even numbers. It wouldn't make sense to try and list them all on a piece of paper, right? So to shorthand things, when you have a really huge set, you use this type of notation. We just make a small sort of outline or description of what numbers we're looking at. So if we have a small set, we might write them out like this and we might list every single number. But if we have a large set that would be way too hard to write, we'll usually use this notation to describe it. Alright, let's take a look at some examples. Example 1. List the elements in the following sets. X such that x is one of the first 5 even natural numbers. Okay, so let's see. First 5 even natural numbers. So what are the natural numbers? These guys right here without 0. And then we want the first 5 of those that are even. So let's see. Let me just go ahead and write out all the natural numbers that I can for a moment. 3, 4, 5, 6, 7, 8, 9, and 10. We might need to write more. We'll see. And then I want the first 5 even ones. So which ones are even? 2, 4, 6, 8, 10. And let's see, how many is that? 1, 2, 3, 4, 5. Hey, there we go. So we have the first 5 even ones. 2, 4, 6, 8, and 10. And there we go. We have that number. That is the set that we are describing. Let's take a look at another one. Where p such that p is a whole number less than 5. Okay, what are we looking at for whole numbers? Well, whole numbers are just like the natural, but they include 0. So let's go ahead and write that down. 0, 1, 2, 3, 4, 5, 6, 7, and so on. And we want the ones that are less than 5. So the ones that are less than 5, not equal to 5, are going to be these ones right here. We'll go ahead and write that set down. And we get 0, 1, 2, 3, 4. Alright, let's take a look at the next example. Example 2. Use set builder notation to describe the following sets. Okay, so that's when we're going to go ahead and set up our variable, so x, such that, and we have to think, how could we describe this set here? Now, there are multiple different ways to describe sets, so there would not be one right answer. But let's see, what do they all have in common? Well, there's no 0, so I would say these are natural numbers, right? And then notice they're all odd. Let's see, 2, 3, 4, 5, 6, 7, 8, 9. Hey, these are all the first odd natural numbers up till 9. So this would be, so x such that x is, and we're talking about these guys, we're calling them x. X is the first, let's see how many, 1, 2, 3, 4, 5, 5 odd natural numbers. Okay, so it's sort of a way of describing that set. Now go ahead and try to describe the set from part B. Okay, well let's see, looking at all of these, they're even numbers. They could possibly be in the natural set or the whole number set. So either one, remember there's no perfectly one right answer. I might describe this as x such that x is an even whole number between and including 4 and 8. That's a super long way of writing it. There are probably simpler ways, but that's a way of describing it. So now let's look at something for the absolute value. So, if you have the absolute value of a number a, you can split it into two options. That'll equal either a if a is greater than 0, or the absolute value of a is going to equal the opposite of a if a was originally less than 0. Let's take a look at some applications here. Example 3, simplify and find the absolute value. Absolute value of 1 minus 3. Well, let's just go ahead and simplify that first. So 1 minus 3 is going to be negative 2. And then the question here. The item on the inside is negative, so it originally was less than 0, which means we're going to take the opposite of the value inside. So what's the opposite of negative 2? That is going to be positive 2. And there we go. Usually people just skip that in between step and go straight to there. But that is sort of a description on what happens. Okay, let's take a look at the next one. Absolute value of 2 minus pi. You know what? I can't actually do the subtraction like I did before. I can't actually get that subtraction, so I need to think here. To get it out of the absolute value, I need to determine, was this originally positive or is this a negative number? 2 minus pi. Let's take a look. Remember, the approximation for pi is about 3.14. So 2 minus 3.14 is going to end up being some negative number. So I know that this number, even though I don't know the exact value for this number, I do know that it would be a negative. So to drop the parentheses, I need to take the opposite of what's inside. A way I think of it is, before you leave the house, if you have a negative attitude, you should change it to a positive attitude. Okay, so we know that originally it's negative, so we're going to go ahead and take the opposite of what's on the inside. And we can simplify that to negative 2 plus pi. And there's our answer right there. Now let's look at C. We have x minus 5. Ooh, here's something fancy. If x is less than 0. So once again, we're going to do this questioning we did here. Is that value on the inside positive or is it negative? And that will determine the way I write my answer in the end. Well, we're told that the x values are less than 0, which means they're all negatives, right? So we have a negative number, so a negative number minus another negative number, which means all of these possible numbers that we could ever get are going to be negative, right? There's no way they could be a positive number. Okay, once again, I know that these are going to be negative values. All right, so I'll go ahead and rewrite this because I know they're negatives. I'll write that x minus 5 is going to equal, or absolute value of x minus 5 is going to equal the opposite of whatever's on the inside. Once again, why did I choose that it should be the opposite? Because I knew that the inside values were negatives. And then I could simplify that to negative x plus 5. Alrighty, and once again, distributing that negative to all of the values when we have the parentheses, same as I did here. Okay, last one. Y plus x if y is greater than negative 4. Okay, if y is greater than negative 4. So out on the number line, we have 0, and then we have, let's see, negative 4, negative 3, negative 2, negative 1, 1, 2, 3, 4, and so on. So we know all of my values are negative 4 or greater. And as usual, when I'm trying to rewrite something without absolute values, I want to discover if it's positive on the inside or negative on the inside. Well, if I was to pick a number greater than negative 4 and plug it into this, what would I get? Let's see. Let's just pick negative 4. Well, y plus 6, if I choose y to be equal to negative 4, that'll be negative 4 plus 6, which is going to be 2. Well, that's a positive number. How about 0? So that'll be 0 plus 6, which is going to be 6, also a positive number. In fact, if I picked any value greater than negative 4 and I plugged it into here, that number would end up being what kind of a number? Positive. Yeah, okay, so we know these are going to always be positive values. So since I know it's always going to be positive, I can write my answer as y plus 6 is going to equal y plus 6. I don't need to change anything because it's already positive. And that would be my answer. All right, that is it for R.1. Please email me if you have any questions.